Okay, picking back up, what if we transform e to the at? What you want to memorize is that will be 1 over s minus a. I'm not going to prove it. I'm not going to work that integral out, but we'll take it on good faith that it is true. If you were to integrate sine of kt in this same fashion, this might be a little surprising. You'd get k over s squared plus k squared. K over s squared plus k squared. And finally, the last one that we need to memorize is the transform of cosine of kt. That will be s over s squared plus k squared. And guys, if you just memorize those, you're going to be in such good shape. This is such a mechanical part of the unit right now. What they're going to ask you to do time and again is just to break some of these down. So I'd like to show you how these things in the box right there could definitely help you. So I apologize, I don't have examples already written out because I didn't have the LaPlace Transform tool on my software. But you could hastily write this out. Example given, the transform of e to the negative 4t. Well, as we look at this, we could say, well, look at a. Guess what a is? A would be the number negative 4, wouldn't it? So as we're looking over here, we'd say, well, very simply, and once you've memorized this too, you'll be able to do this so quickly. You'd say that's 1 over s minus negative 4. That's 1 over s plus 4. And you're done. You come over here to this next one, the LaPlace transform of 3 plus 2t squared. Well, that we can break apart. The LaPlace transform of 3 plus, tell you what, any coefficient, you could even pull that out. By the way, I could have pulled the 3 out and just done a LaPlace transform of 1. Could have done it that way too. But hey, look at this. Maybe you remember what the LaPlace transform of a constant was. And I'm talking about the Laplace transform right here. The Laplace transform is something just like 3. It would be 3 over s. Whatever k is, you go k over s, right? So we're going to say this is 3 over s plus, we've got our 2 out in front. Well, now we're going to have t squared. Look in the top left corner of the screen here. Talking about this thing right here. We're going to have a factorial. What factorial up on top? 2 factorial. Down below, I'll have s to the 3rd. Final answer is going to be 3 over s plus 4 over s to the 3rd. You don't have to get a common denominator. In fact, it's probably better that you don't at this point. We doing okay so far? Once you know these transforms, you just have to plug them in and make some sense of them. Let's take a look at the Laplace transform of 5 sine of 3t minus 17e to the negative 2t. And of course, you could pull the 5 and that minus 17 out in front. After a while, kids get so comfortable with it, they don't even bother pulling them out. They'll just say, look, I know a 5 is going to go out in front of my transform. And this is your k. Your k here, would we agree, it is 3? That's the number in front of your t. And then what? Then you just come right up here and you'd say, well, how do I transform the sine of kt? Answer, it's k over s squared plus k squared. So it's going to be 3 over s squared plus k squared. And of course, we know that 3 squared there is going to become a 9. Then we could say minus our 17. Our a here is negative 2. So if we were to go back to our e to the negative 2t, Take a look at this transform with e to the at here. It's going to be 1 all over s minus negative 2. Cleaning this up, you'd get 15 over s squared plus 9. This is minus a 17 all over s plus 2. You could leave your 15 and the minus 17 out in front of that just as well. Guys getting the hang of it? Just takes a little getting used to. You look right here, you'd say, well, gosh, look, I've got 2 sine of t. By the way, you want to think of that as the sine of 1t. You want to look at that as if k equals 1. Here we get k equals 2. So as I do this transform, I'll have my coefficient out in front. There's my 2. And the sign, if you look in that box, it's still highlighted in blue. I'm going to say, well, I should have 1. That's your k, right? All over s squared plus 1 squared. Here I'll have my 3. And the transform for cosine is the last thing in the box. We'll have s over s squared plus 2 squared. And guys, you'll get so comfortable with this, and I bet a lot of you are comfortable enough already, where you could just say, oh my gosh, I don't even need to break it down the way you just did. Final answer would be 2 over s squared plus 1 plus 3s over s squared plus 4. Okay. Finally, we've got this last problem that we're going to take a look at. And what can seem a little frightening at first is the fact that we've got a piecewise function. So we could do this LaPlace transform where f is defined to be 0 in certain locations. That's between t greater than or equal to 0 but less than 3. And then it's 2 as t is greater than or equal to 3. And the problem is, guys, as we really begin to go back to this definition, we could say, look, when we're applying this LaPlace transform, we're going to integrate 0 to infinity of e to the negative st of f of t dt. And here's the problem. The function changes as x, or in this case t, I am so sorry, as t goes from 0 to infinity. So guess how many integrals I'm going to have to write? 2. I cannot do a LaPlace transform with the memorized forms that we had earlier. Sad to say. But we can say, look, we can say we're going to go between 0 and 3. But, oh, look at this. F is just 0 then. Oh, I kind of like that, don't you? That 0 is going to wipe that whole integral out. And then you're going to say, well, now you're going to integrate from 3 to infinity of e to the negative st 2 dt. Please realize I cannot use my shortcut that we had, the Laplace transform of k being k over s. It's so tempting to say, hey, it's 2 over s, we're done. No, the Laplace transforms that I'm asking you to memorize go from 0 to infinity. 0 to infinity. Okay, so like I said, this first integral is going to be gone. And as we're working this out, let's do a real quick antiderivative. We know we have a 2. We'll have an e to the negative st, but we have to reverse the chain rule. So we're going to have to divide by negative s, right? Yes. Why don't we write a constant? Well, because this whole thing right here is completely, okay, a question arises with the first integral. Why don't we just put a constant out? Look, if the inside is really 0, let's go back to net area. You're saying from 0 to 3, find the net area when you'd have like y equals 0, right? And of course, that would just be a 0, right? Okay, but as we're working this thing out, so we're just trying to finish that, Once again, I mean, we could say here's negative 2 over s, and, this would be e to the negative infinity minus, here's e to the negative 3s. But we talked about what e to the negative infinity is. That happens to be 0, because when you look at the graph of e to the x, we can see that, that thing's going to be going to 0. So what's your final answer going to become? Negative times a negative is a positive. Here's 2 over s. You could leave that as e to the negative 3s. Once again, you can't use your shortcuts, but you can still work it out with basic calculus. Okay?